Section 11.2, Special Cases and Relative Motion. We're going to go through a couple different scenarios in this part, and they're all going to fall back to just v equals dx over dt and a equals dv over dt. First scenario is where we have constant velocity. So picture a situation where you have constant velocity. Driving down the highway, put your cruise control on, what do you say, 60 miles an hour, Texas, so 75 miles an hour. So constant velocity, you're not speeding up, you're not slowing down, acceleration is equal to 0. So what equations would go with something like that? Well, we're going to go to our favorite starting point, okay, v equals dx dt. If that is constant, what does that look like? Okay, so we can rearrange it. V dt on one side, dx on the other side. So we have change in position is just our velocity times time. Or you can rearrange this to just look like it's just a line, right? So y equals b plus mx, x equals x naught plus vt. Velocity is the slope of this line, and this is a slope, right? V equals dx dt. It's change in position over change in time. It's linear. And if you want to know how far you've gone, just multiply your velocity by your time. And you can look at the units on this too. What are the units for velocity multiplied by time? We have something like miles per hour times hour. So miles over hour times hour, you get miles out of that. You get a position. Check your units. If you're ever confused, if maybe you didn't get the equation right, if your units work out, you're halfway there. Okay, so pretty simple scenario. Constant velocity, and this is the equation that's going to go with that. Just your position is changing linearly with time. Next scenario, constant acceleration, and this is a pretty commonly found scenario. What you'll usually see is gravitational acceleration. So most of our problems will be on Earth, and we have gravity, so we're always going to be dealing with things falling under gravity. So this is another common one. What are the equations that would go with this? Okay, so come back up here to our favorite equations. What can we start with here? Okay, a equals dv dt, and this is going to be constant. So if we put velocity on one side and time on the other side, here we have, it's kind of similar, right? Only now it's velocity that's changing linearly with time instead of position. So our velocity is changing linearly with time. This is just, another y equals b plus mx. It's just a line. And in this case, the slope of our line is acceleration. So the slope is change in velocity over change in time. And you can do a units analysis on this too. So what are the units for acceleration? 9.81 meter per second squared. You have the second squared, a time squared on the bottom. So if you do meters per second squared times second, you get meters per second. You get some kind of a distance over time unit going on here. Okay, so linear velocity. Are there any other equations that would go with constant acceleration? Well, if we have velocity here, let's come back up to our favorites. Velocity is also dx dt. So what if we want to create an equation down here for what position is doing with time too? Okay, so I can set v naught plus at. I can set that whole equation equal to dx dt over here. Okay, so here's velocity equals v naught plus at, only now we're going to solve for our position. So we can walk through here. That at, this is where you get your 1/2 at squared. And you've probably seen this equation before, but remember where these guys come from. You don't have to memorize anything if you can just remember where it comes from, and knowing where it comes from will remind you what you can use it for. Okay, this equation, it only works if a is constant. That's a common mistake, is to just slap this equation in there when you don't have at constant acceleration. So make sure you know how these things were derived and what situations they actually apply to. Okay, is there anything else that we can do? Any other equations that we can do for constant acceleration? I should have put one more equation up here. I should have put this little guy. So instead of a dv dt, remember how we can split this apart? You can split it into dx dt and dv dx. So just a little chain rule there. And then dx dt is velocity, so acceleration is also v dv dx if we want to see how acceleration changes with position. So if we use this other definition for acceleration, what do we get? Acceleration is constant, so this is where we plug in 9.81 or whatever constant acceleration we have in a situation. Group all of your velocities together, and then we can put a dx on the other side. So you get 1/2 v squared. You can pull the 2 out and put it next to the a. So here's another equation that relates velocity to position. So we have velocity, acceleration, time, position, velocity, time, acceleration, and velocity straight to position. You could all of these work for all the constant acceleration problems, but you're going to want to choose the one with the fewest variables. So sometimes this little last guy is the fastest way to go. You don't have to mess around with figuring out what time is. You can just straight up relate your velocity, acceleration, position without worrying about time. So that becomes pretty convenient to use. Okay, so we have constant velocity, constant acceleration. One more special case we're going to look at here, and that is instead of just keeping track of one thing moving around, we're going to keep track of several things moving around and how they're moving relative to one another. And within looking at the motion of multiple objects, there's going to be two different scenarios. One is everything that's moving around is not dependent on one another. They're not tied together. They're not changing one another. And the other scenario is dependent motion. So independent motion, that would be like these two boats. There's not a rope between them. There's no magnetic fields between them or something. They're just whatever boat B is doing has no bearing on what boat A is doing. They're independent of one another. They're not connected to one another. The other case is dependent motion, and this is if A is moving around, that's going to cause B and C to move around too. They're tied together, so the motion of one is going to change the motion of other. Now, these guys are not maybe moving at the same rates as one another, but they are tied together, and you can write equations to show how the motions of each of these guys are related. So that would be dependent if they're somehow connected through some interaction potential or a rope physically connected to one another. That would be dependent motion. So two different, and this looks at relative motions of objects. Constant velocity. Let's just think through a scenario with constant velocity. So here's one scenario. You're headed out on a road trip, going to leave Houston and maybe spend some time in San Antonio. Fun little city, you got SeaWorld out there, the Riverwalk. Okay, so from Houston to San Antonio, pretty straight shot, nice straight road. Put your car on cruise control. We'll pretend like there's no traffic out there. Have the cruise control set to 75 miles an hour. So what would this road trip look like on a graph? So we're going to plot our position over here on the vertical axis and then our time here on the horizontal axis. We can let's call Katie point 0, okay? So that's point 0, that's where we're starting, and we go drive down the highway, okay, and there's time that elapses. So you can ask yourself, how long does it take for me to travel 40 miles, okay? How long does it take me to travel 60 miles? So as you're traveling down the highway and getting farther and farther, that's what that graph looks like. Now this is, we'll pretend like it's just a nice straight line. And here's some questions to ask. where is the velocity on this graph? You want this to be intuitive, that you don't even have to think about it. Okay, so where is the velocity on this graph? Velocity is dx dt, rise over run. The slope of this line is your velocity. So when you have some kind of a position versus time graph, when you're seeing that slope, if it's a changing slope or a constant slope, you're watching how that velocity changes. Even though this isn't a graph of velocity, you can get velocity information off this graph. Okay, what does a graph of velocity versus time look like? So this is position versus time. What would velocity versus time look like in a situation where you have constant velocity? Here's the graph of velocity versus time. It's not very exciting. It's just a straight line. So we start out at 75 miles an hour. Half an hour later, we're still going the same speed. An hour later, we're still going the same speed. So it's just constant, flat velocity. And the value here is, that's the slope of your position versus time curve. How far has the car gone in 1 hour? And this seems like a pretty silly question to ask, but it'll solidify slopes of lines and areas under curve. Okay, so if I want to figure out how far the car has gone in 1 hour off of my position graph, how would I figure that question out off of my position graph versus if I want to answer this by looking at my velocity graph? How would I find position on my velocity graph? So here we go. If I want to answer how far the car has gone in 1 hour from my position graph, what we're going to do is we'll come over here to 1 hour, and then we can walk up and say in 1 hour we have gone 75 miles. Okay, and that makes sense. It's pretty obvious. So it's just right here on the graph. But if I want to know how far I have gone according to my velocity graph, how can I figure that out? By just looking at velocity versus time. And for this, okay, do you remember how to calculate the area of a rectangle? What's the area of a rectangle? Area is just base times height. Why am I asking this? Well, we've got a rectangle here, okay? So constant 75 miles an hour, and then that's the height of our rectangle, okay? So the height is our velocity, and then the base of our rectangle is time, okay? So base times height, times velocity. What are the units on this? So when we multiply the height of our rectangle, which happens to be velocity, times time, okay, the time cancels out and we end up with miles, position, okay? The area underneath the velocity versus time curve is your change in position, okay? This is the area under the curve. And once again, just look at the units on this thing. Okay, if the units work out correctly, then you're good. So the area under the velocity versus time curve is your change in position. The slope of your position versus time curve, that slope is your velocity. So that's, you go back and forth between these two graphs. Here's a little bit more realistic of an example in that we don't have a straight linear line. We have steep slopes and shallow slopes. We're speeding up and slowing down. If you were given this graph, could you identify where there was a traffic jam? Where the velocity was the fastest? Could you sketch the general shape of the velocity versus time graph just by looking at the shape of this line? So not using an equation, but looking at the shape of this graph. Let's answer the first question. Where is traffic the worst? when you're watching how this slope changes, you're watching how the velocity changes. So look at where the slope is shallower and smaller. So this is where there would be traffic going on at these smaller slopes. Where's the velocity the fastest? Again, just look at how this slope is changing. Where is the slope the steepest? So that's where the velocity would be the fastest. Next, what would the velocity versus time graph look like? And you don't have to visualize the whole graph at once. Just take it one piece at a time. So let's look at the very beginning. What is the slope at the very beginning? So it's kind of steep at the beginning. So we'll start with a rather large slope. And is that slope getting steeper or is it getting smaller? See how we're headed to kind of a flatter area? The slope is getting smaller. So we start with something big and the slope is getting smaller. Can you picture what the next section looks like before it's revealed? The slope continues to get smaller and smaller. It's still positive. It's still increasing, but the slope is getting smaller. We're slowing down. How about the next step? Slowing down, and it looks like somewhere in here we're getting a minimum. There's an inflection point in here. Because after this point, what happens to the slope? Now the slope is starting to get larger. So our velocity is getting larger. So the key thing to look for in these graphs are inflection points and mins and maxes. Okay, so what does this last little section look like? What's happening to the slope? Is the slope getting larger or smaller? So here we're getting smaller again. Even to the very top, the slope actually goes to 0 at the top and starts coming back down, which would be a negative slope, or turning around and going the other way is what that would physically mean. So for these graphs, just take it one little piece at a time and walk from point to point, slope to slope, and visualize what is happening in each time period in these graphs. There's position, velocity. What's acceleration going to look like? Okay, so our velocity graph is a little bit more complicated than even our position graph because we have negative slopes, we have positive slopes, we have 0 slopes. So this is going to be even more interesting to try and walk through. See if you can do this before looking at the answer. So if you were to sketch the acceleration graph, what would that look like? And the same thing for this one. Just take it one little piece at a time. Okay, so this time we have velocity at the top, and we're going to go from velocity to acceleration. And remember, acceleration is the slope on that velocity curve. So here we go. What's happening for this first chunk? Is the slope positive or negative? That's a negative slope. Is it getting steeper or shallower? Okay, so we have a negative slope, and that negative slope is headed to all the way to 0 over here, right? So initially it's really steep, but it's headed to going to 0. So here's this first. So we start with something really negative, but then it's headed up to, eventually it's going to be to the positive direction. Okay, there's the first chunk. What's the next chunk look like? There's the next chunk. This is all negative. So here's our 0, and everything underneath there is negative. We're going to go from a negative slope to a positive slope here. So this next little chunk is all in the positive side. This is all positive. And there's an inflection point. It gets steeper, 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 and then it's going to start slowing down back to 0. So you can see where those two 0 points happen, where it's crossing that 0 mark. You can see where is the slope positive versus where is the slope negative. And the next little chunk, the last chunk, is all negative, and it goes from just flat and 0 to getting steeper and steeper and steeper. So there's the last little chunk. It's negative, and it's getting steeper and larger as we go. There's all three of them together. Okay, now what these graphs are telling us, and this is a little sneak peek for things to come, what physical quantities are dependent on position? Position, that's mgh. H is position, your potential energy, or if you're looking at a spring, 1/2 kx squared. X, that's a position of how much that spring is stretched out. So when you're looking at the position graph, that's looking at how your potential energy is changing with time. You can also think of position as it's related to work. So work is force through a distance, F dx. So by visualizing that position graph, you're also visualizing how much work the system has done. Velocity. What quantities are dependent on velocity? 1/2 mv squared, kinetic energy. So when you look at that velocity graph, you're seeing how the kinetic energy of the system is changing with time. Or you can think of velocity in terms of mv, momentum. So that's, you're seeing more than just velocity here. You're seeing impulse and momentum, you're seeing kinetic energy, and if you know how velocity and position are related to one another, you can understand how kinetic and potential energy are related to one another, how work is related to everything. Last one, acceleration. The big Newton equation, F equals ma. So what kind of unbalanced forces are we talking about here? And this is, F equals ma is an interesting equation. We've looked at force balances in statics, and if the force is balanced to 0 or not. ma on the other side, this ma is not really a force, it's a motion. Okay, so you almost don't want to say it's equal to one another. The magnitudes are equal, but ma, that's describing how it's moving around when the forces don't add up to 0. And if you can see how the acceleration relates to velocity and position, that's understanding how those unbalanced forces relate to your energies, relate to the work going on, and understanding how all of this stuff is interrelated. That's pretty much what dynamics is about. Let me just go through a little bit more for this F equals ma. So F equals ma, acceleration, that's change in velocity versus change in time. You can do a little chain rule here where you can add in a dx. So this turns into mv dv dx, and if I take the position to one side and keep everything with velocity on the other side, let's say our force is mg, let's say just gravitational acceleration, and our change in position, let's call that dh. So you can see where this went. This just turned into potential energy to kinetic energy, energy balance. So the acceleration is related to velocity, it's related to position, and that comes off of these three graphs here. Or let's say we didn't use the chain rule, so acceleration, we just keep acceleration as dv dt, and we pull that time over to the left hand side. Force through a short time, that's called impulse, and then mdv, that's momentum. So we'll do some impulse and momentum when we look at collisions. Again, you have acceleration, you've got velocities. So these three graphs are where it all starts to visualize how all of these quantities are related to one another. So really study them and get intuitive for how these are relating to one another. So we went through constant velocity situation with cruise control. Now let's head down and look at some constant acceleration problems. So this would be where we have just gravitational acceleration for falling objects and situations like that. And remember, for our constant acceleration situations, we're going to be able to use these are the three main equations, and they are derived from A equals dv dt. Okay, so there's our linearly changing velocity, constant acceleration, constant slope on the velocity curve. Acceleration is the slope of velocity. We also have our position dependency, so no longer linear here. 1/2 at squared. That t squared is going to give us a non-linear position versus time graph. And we also have this relationship between acceleration, velocity, and position. If we don't want to worry about the time, we can grab this last little relationship here. Here's a constant acceleration example. So what we have is a ball that's being tossed out of a window of a building. Okay, so the window is 20 meters up. Leaning out the window, and we're going to toss the ball up in the air, and the initial velocity of that ball is 10 meters per second straight up. So we have an initial velocity of the ball going straight up. We're going to toss it up. It's going to slow down to a stop because of gravity, and then it's going to fall back down to the ground and hit the ground. What we want to find is the maximum position. So how far up does it go before gravity pulls it back down? How long before it hits the ground? So how long does it take to go up and then crash down to the ground again? And what velocity does it hit the ground with? Okay, is this really a constant acceleration problem? Because what's happening on the way up? On the way up, it slows down to a stop. So it's slowing down, and then after it reaches the highest point, it's going to start slowly and then go faster and faster and faster until it hits the ground. So it's slowing down and it's speeding up. If you see something slowing down and speeding up, that doesn't sound like constant acceleration, does it? Remember, acceleration is not change in speed. It's change in velocity. What's the difference between speed and velocity here? Speed is not a vector. Speed has a magnitude but no direction. Acceleration is change in both direction and magnitude. So even though the speed is changing here in that we're slowing down and then we're speeding up, even though the speed is changing and doing different things, acceleration is constant. What is acceleration the entire way through here? It's nothing but gravity. To visualize what acceleration is, don't think about speed. Think about the forces acting on the system. F equals ma. Acceleration is what gives force its direction. Mass is not a vector. Mass is just a scalar multiplier. So the direction of force and the direction of acceleration, those are going to be one and the same. So if you can visualize the force acting on the system, that will tell you what acceleration is acting in the system. So in this case, the only force after this ball leaves his hand, and it's just sitting here in thin air, the only force that's acting on it through this entire trajectory is nothing but mg. It's just gravity. So if you can see that the force is constant through the whole thing, that will tell you that acceleration is constant through the whole thing. That's one of the confusing points that gets people every time, is like you think you're accelerating your car, you're speeding up and slowing down, and acceleration is not change in speed. It's not change in speed. It's change in velocity, and those are two very different things. Scalar versus a vector, very, very different things to think through. So visualize acceleration by visualizing the forces acting in your system. Here's the equations we have for constant acceleration. Our velocity is going to be changing linearly with time. Position, there's that squared. What's the position going to look like? It's going to come up in kind of a parabola with that squared. And then you also have your velocity position. Once again, let's look at the graph and think through what this graph is telling us. So let's start with velocity versus time. In this case, we have constant acceleration, which means our velocity versus time graph is linear, and the slope of this line is acceleration. Think through physically what is happening here. So what's happening at t equals 0? T equals 0, that's when we first throw the ball out the window. And what happens to the velocity after it falls? So we go up and slow down, and then start speeding up, and then we hit the ground. Okay, so we start with a positive velocity going up, and then we're going to slow down, and at the very top, the velocity goes to 0. It stops. And then on the way back down to the ground, the velocity is going to get more and more negative. So right here where it crosses the axis, this is the turnaround spot. So the velocity starts going up, it slows down to 0, and then it starts speeding up, and then it crashes into the ground down here. So hopefully you can see what's happening with speed versus what's happening with acceleration, and how acceleration and speed, those are different things. So the magnitude changes. It slows down to 0, and then it speeds up. Okay? But just because it's slowing down and speeding up, the slope of this line is still constant. It's just a straight linear line. So speed has changed. Acceleration, the slope of the line has not changed. Acceleration is constant. Now we were asked, what is the highest point the ball will reach? Here's our position versus time graph. So our ball comes out of the window, it goes up, and then it crashes back down to the ground. It's actually going just in a straight line, straight up and straight back down. So it goes straight up and stops, and then it takes some time to come back and fall to the ground. We want this point right here. Here's our position equation. So we have that 1/2 at squared vt. There's two unknowns here. We don't know what time it happens at, and we don't know the position it happens at. So we have two unknowns. We need two equations. So to figure out what the max position is, we have to figure out what the time is. And to figure out what the time is, we have to look at the velocity curve. So max position, look at the velocity curve. And then from the velocity curve, find when this velocity goes to 0. And when we can find when that velocity goes to 0, that's the time our position is at a maximum. So you really have to bounce back and forth between these two graphs. You can't solve for position straight from the position graph. There's too many unknowns in here. You get your position by first looking at what's happening velocity-wise. So it's you bounce back and forth between these guys, and it's, you know, you've got two equations, two unknowns. You can solve for your time, and once you have your time, then you go back up and look at your position. So here is solving for the time. We're just going to plug some numbers in. Our initial velocity was 10. Our acceleration was 9.81. It's negative. Gravity is pulling down in the negative direction. And we're going to set this equal to 0. So when 10 minus 9t equals 0, what time does that happen at? You're just setting the whole equation equal to 0 and solving for t. Okay, so once you solve for t, what's the next step? You're going to plug this time into your position equation, okay? So there's some times in there, you just plug it in. So here's vt, 1/2 at squared. You just plug those times in, and then you can figure out when your position is a max. The last scenario here is the motion of several particles at once. We'll look at independent motion and then dependent motion. So those are the two different scenarios. We'll look at relative motion too. Motion of several particles relative to one another. Here's the nomenclature. So if you see VA/B, this is meaning A is relative to B, or A as seen by B. Okay, and this is always confused, what's relative to what. Usually when we measure velocities, like this boat is going 20 miles an hour and this boat is going 10 miles an hour, but what are they relative to one another? This velocity is relative to something. We're used to measuring velocities relative to the water, relative to the road, relative to the earth. Okay, this isn't relative to the sun or relative to the other boat, but it's, you want to see how fast are they catching up to one another? Who's going to win the race? When are they going to pass one another? So we want to see not just relative to the water, we want to see what are the velocities relative to each other. And to do that, one of the easy ways to do that is to kind of get rid of the water, okay? So we're not thinking of anything relative to the water anymore. So pretend like the water doesn't exist. You can think of it as boats in outer space instead of boats on the water. So you can't see the water anymore. You can't measure your position relative to the water anymore. Now you're just measuring your position. The only other thing you can see is the other boat. Okay, so let's say you are sitting in boat B, relative to B, velocity of A relative to B, and from B's point of view, so remember you can't see the water, the only thing you can see is the other boat. And what does it look like that other boat was doing? Well, initially, if you were going 20 and he's only going 10, you're catching up with him, right? And what that looks like, if you're in outer space and you can't see the water, you're going to pretend like B is stationary and everything else, the whole universe, is just moving with respect to B, moving around B. So in this case, if you look at A, it would look like A is getting closer to you, okay? So the relative velocity from B's perspective would be A looks like it's actually moving backwards in the negative direction. And you do that vector analysis by saying VA relative to B, that's velocity of boat A minus velocity of boat B. It's just the difference between what those were both doing with respect to the water. Okay, so A was only going 10, B is going 20. 10 minus 20, you get negative 10. Hopefully that makes sense. So from B's perspective, it looks like A is going in the negative 10 direction, and pretty soon A is going to back up into B, is what it looks like if you don't think of it relative to the water. Velocity of B relative to A. So we're going to switch which boat you're sitting in. So now you're sitting in A, and from A, you're looking back at B. Okay, and if it's relative to you, you are now the center of the universe. So pretend like you're the one sitting still and everything else is moving around you. Okay, so if you're the center of the universe, what does it look like B is doing? Again, B relative to A, this time we have B minus A, 20 minus 10. So it looks like B is catching up with you. And it's catching up with you at 10 miles an hour. This time it's positive. It's going to the right. It's going to ram into the back of you. So from A's perspective, relative to A, it looks like B is moving forward at 10 miles an hour. So really think through how these vectors are going to be written. B slash A, that's relative to A, and the vector equation here is going to be the velocity of B minus the velocity of A. So just B minus A. Here's an example problem. Let's go ahead and read the problem statement, and you'll get through these a lot faster if you really visualize and understand the scene that's going on and what motions are going on. So think through what this means. In a boat race, boat A is leading boat B by 50 meters. Okay, we have some information here. 50 meters. Where is that on our picture? 50 meters. So A is leading B. It's in front by 50 meters. There's some velocities drawn on here. They're traveling to the right. Okay, A is leading B by 50 meters. Both boats are traveling at a constant speed of 100 kilometers per hour. At time equals 0, the boats accelerate. They both accelerate at constant rates, knowing that B passes A after 8 seconds have gone by. So they're both going at a constant rate, and then all of a sudden they both see something out here and they both want it, right? So at time equals 0, they both step on the accelerator, they both start going as fast as they can, and 8 seconds later, B passes A. So B can accelerate faster than A. And when they're past one another, there's the velocity of A after they pass one another. So you want to figure out how fast A was accelerating and how fast B was accelerating. So B was accelerating faster than A, it catches up. We want to know their relative accelerations from this information. How do we solve problems like this where we have two different objects? Each object is moving independently of one another. We have velocities and accelerations going on for each object, and then what you do is you're going to split it up. First, ignore what B is doing. Just get rid of B and just gather all the information you can for A. Just figure out as much as you can for what A is doing. Then once you have equations and information for A, then you're going to ignore A and you're just going to walk through and figure out what B is doing. So ignore the rest of the world, zoom in on just this one little piece and figure out what B is doing. Okay, so if it was a problem with only one boat and they gave you velocities and information for one boat, you could do it, right? So it's more of the same thing. You're just keeping track of different pieces of it. So you calculate what A is doing, and then you go and whole nother problem, calculate what B is doing. And then the third piece is you're going to compare A and B to one another. So what's their position relative to one another? What's their velocity relative to one another? And it's just subtracting one from the other. So here we go. What is A doing? What information do we have? What equations can we use? Well, we start with a constant velocity and we accelerate at a constant rate. This is a constant acceleration problem. So that simplifies it. Let's get out our constant acceleration equations. Okay, so for constant acceleration, we have things like velocity of A is the initial velocity plus acceleration of A. So we need to find the acceleration of A. Okay, that's right here. And we're given the initial velocity of A. And we're given the final velocity of A. So which piece of this equation do we not have? The only piece of the equation we didn't have was the acceleration. Okay, so 8 seconds, the velocity of A goes from 180 to 225. So 225 equals 180 plus A times 8 seconds. So acceleration is the only thing we don't know. We can plug in all of these. Yeah, watch your units on this. So we have time is in seconds and velocity is in hours. So you have to switch that over from kilometers to hour to meters per second. Watch those units, and then once you have everything in the right units, you can figure out what the acceleration of A is. Next step, we're going to start looking at B. What is B doing? They both are accelerating at constant rates. This is acceleration problem for both of them. So here's the position of B. So initially, let's call this a position of 0, and then let's say A starts with a position of 50. So B starts at 0, A starts at 50, and then at 8 seconds, those two positions are equal to one another. That's where they pass one another. Okay, so we have an equation for each of those. We can set those next to one another. So here's A. A starts 50 meters ahead. There's velocity of A changed to meters per second, the time they pass. We found the acceleration of A. There's the time again. So that's the position where they pass one another, 500 meters out. So now that we have that position, we can plug this position into our equation for B, okay? So after B has traveled 500 meters, we start at 0. Here's the initial velocity of B, 8 seconds out. The only thing we don't know in this equation is our acceleration. So now we can solve for the acceleration of B. So that's how you do the independent motion. Look at just one little piece of it, figure out what one piece is doing. Then you look at the other little piece, figure out what that other little piece is doing. And then you start comparing one to the other. When do these guys have the same position? What does their velocity look like relative? So I could say VA minus VB or VB minus VA. I can look at their relative velocities to one another. But it starts by just looking at the individual boats all by themselves. Here's another example. Examples are a lot of times the best way to learn this stuff. Each one is its own little puzzle, but there's some similarities between the problem. For this example problem, we have an elevator. So here's our elevator going up and down in the elevator shaft. And we also have a ball being thrown around. Okay, so a ball thrown vertically from 12-meter level in an elevator shaft with an initial velocity of 18 meters per second. So the ball, the initial position is 12 meters up, and it gets thrown up with 18 meters per second. At the same instant, an open platform elevator passes the 5-meter level. So here it is, it starts at 5 meters up at time equals 0, and the velocity of the elevator is 2 meters per second up. Okay, so you have a good picture of what the elevator is doing. Starts at 5, constant velocity of 2 meters per second up. The ball starts at 12 meters and starts with a velocity of 18 meters per second. And it's just flying around in air up here, so gravitational acceleration. Determine when and where the ball hits the elevator and find the relative velocity of the ball and elevator at contact. Okay, so when are the elevator and the ball going to hit one another, and bam, how hard is that ball going to hit? So what's the relative velocity? For all of these equations, you're going to split it into parts. Let's start by just considering the motion of the ball. Just the ball, we have constant acceleration, gravity is acting down. So here is our constant acceleration equation. Velocity of the ball equals that initial velocity plus acceleration times time. The initial velocity was 18 meters per second. Acceleration is gravity, so we're going to plug that in there. So there's our velocity. We can also get an equation for what our position is doing. So here's the position of the ball is the initial position. It starts at 12 meters up. Here's our initial velocity of 18 meters per second up. And we have 1/2 A, 1/2 times 9.81. So we have our acceleration here, t squared. So here's velocity and position of the ball. Next chunk. Now we're just going to consider what the elevator is doing. The elevator has a constant velocity, no acceleration. So our velocity equation for the elevator is pretty boring. It's just a number. V equals 2. Instead of V equals V naught plus AT, it's constant, not dependent on time at all. V equals 2. The position of the elevator, and this is the same as our constant acceleration, only we don't have that 1/2 AT squared. No acceleration, so we end up with just that linear chunk of it. So the position of the elevator, where it starts 5 meters up. plus velocity of the elevator, 2 meters per second times time. Okay, so now we have velocities for each of these pieces and positions for each of these pieces, and we have to figure out where they're going to hit one another. They're going to hit one another where their positions are the same. So when the YB equals YE, that's where they've hit one another. And we can figure out what time that happens at. And when we figure out that time, we also want to know their relative velocities, okay? So relative velocities, whether it's from the elevator's point of view or from the ball's point of view, is going to be the difference of these two quantities, and we'll have to plug in the time where they hit one another. So here we go. The position of the ball relative to the elevator from the elevator's point of view. So that means we're going to have the equation for the ball, YB. That's the one the ball is experiencing gravitational acceleration. So here's the equation for the ball. Subtract off the equation for the elevator, YE. So this is the relative position to one another. And when there's no space between them, 0, this is where they hit one another. So YB equals YE, or that relative position is 0. So we have a t squared, just use a quadratic equation. The only thing we don't know here is time. So we solve this equation and we can find what time they smack into one another. We'll ignore the negative. So after 3.65 seconds, the ball hits the elevator. Okay, next up, velocities. So where do they hit and what are their relative velocities? Where they hit, we can plug this time into either where the ball is or where the elevator is. Either one will give us the same thing. So plugging 3.65 seconds in, the position of the elevator, so it started 5 meters up, it's going to constant velocity. So this is y0 plus vt. Just plug in that time. This is the position where they hit. And that's the position of the elevator or the position of the ball. It'll be the same thing. And velocities when they hit. So relative velocities, let's do this from the elevator's point of view. So velocity of ball minus the velocity of the elevator. So here's what the ball is doing. Again, we're going to plug that time in for the ball because its velocity is changing. The elevator, it has a constant velocity. It's not changing around. So we have a relative velocity, ball minus the elevator, plug in the time. From the elevator's point of view, it looks like the ball is coming down and it slams into that elevator at negative 19.8 meters per second. So this is from the elevator's point of view of that relative velocity. Next up, dependent motion. And it's going to be similar to independent, where we're going to carve it into pieces. So just look at what A is doing. Just look at what B is doing. Just look what C is doing. And then how are they connected to one another? That's going to be the new piece of it, is you're going to look at how they're connected to one another and create equations that show how those motions are related to one another. Dependent motion. Let's consider the case where we have two weights, weight A and B, and they are connected together over a system of pulleys. Okay, so you see how this rope is wrapping from the ceiling all the way down to B, all the way back up to CD, and then down to A. Do you remember these problems from statics? Okay, so how do these guys depend on one another? The trick here is we're going to start with kind of a position equation. We're going to start by just finding what is the length of this rope. And the trick here is the length of the rope is not going to change. So it's not a piece of elastic. It's not getting stretched out. So the length in the A chunk is changing. The length in the B chunk is changing, but the overall length of the rope is constant. Okay, so if we say, what is the length of this rope? Well, from A to C, there's one little piece of it we can add together. And then there's two more pieces. See how from D to E, and F to G, those two chunks are the same length. So the overall length of the rope is these two blue chunks, 2XB, and then the one yellow chunk, XA. And if you add together those three chunks, that's the total length of the rope. As this starts moving around, the length that's over here in the yellow is going to change. The length that's over here in the blue is going to change. The blues are going to change together though. So as B goes up, the blue is going to get shorter, yellow is going to get longer, but both of those blue lines will get shorter at the same rate. What we can do here is we can just see how these are changing. So we're going to throw a DT on here. How is A changing with time? How is that B chunk changing with time? The length of the rope is not changing with time, so that goes to 0. All those go to 0. And we now have the relative velocities of those two weights. Okay, so just by looking at how this chunk of the rope is changing with time compared to how these two chunks of the rope, and it started by just adding the lengths of the rope together. So we take the derivative with respect to time of a position, and there's our velocities. There's our relative velocities, and of course we can go one step further. So take the derivative with respect to time of our velocity, and that will give us our acceleration. So how fast is A accelerating relative to B? And we have a 2-to-1 ratio here. That's the point of pulleys, right? Is you get these little mechanical advantages happening. So we have relative velocities, relative accelerations, and all of these came from the relative lengths of our rope up here. What is the equation that relates the positions of, now we have A, B, and C? Practice makes perfect, so look at a couple of these things, see if you can figure that out. What is holding up C? There's only one cable that's holding up C. Over here to B, we have two cables that are holding up B, and for A, we have two cables that are holding up A. So if we write up the equation that looks at those positions and how the positions are going to change relative to one another, use a highlighter. Sometimes a highlighter is helpful. So yellow cables, those two guys are holding up A, so we have 2XA, two little pieces of rope here. Green for B, so two little pieces holding up B, and then C is the last one in the blue. And if we add all those chunks of rope together, we get a constant. Now, I guess this isn't quite the length of the rope. This little piece, that length will never change, or up to the ceiling won't ever change. So all these little chunks that don't actually ever change, we're going to just group all of those over here to kind of the length of the rope and anything that's constant. But these are the pieces that are going to be changing with time. Okay, so we have those relative positions. That turns into relative velocities and relative accelerations, 2XA to 2VA to 2 acceleration A. So now we have relative velocities of each of those pieces and relative accelerations. Now for this one, since we have three objects moving around here, that's going to give us 2 degrees of freedom. We're going to need a little bit more information to solve this. If we know the motion of A, we cannot solve for the motions of B and C. We need to know both A and B or both A and C. We need to know what 2 of these things are doing, and then we can solve for what the third one is doing. So that's, you have to have 2 pieces of information, 2 degrees of freedom to solve for these problems. One more example, and there's another example in the notes too. So here we have 3 objects, kind of like the previous one. We have 3 objects. Pulley D is attached to a collar, which is pulled down at 3 inches per second. At t equals 0, A starts moving down from K with a constant acceleration and 0 initial velocity. Knowing that the velocity of A is 12 inches per second as it passes L, so it's going to start moving down and then it's going to pass L, Find the change in elevation, velocity, and acceleration of what B is doing when block A is all the way down at L. So we know what A is doing, we know what D is doing, and from these two pieces of information, we're going to work our way back over to figure out what B is doing. So this is a system with 2 degrees of freedom here, so we need the information from 2 pieces of it. For all of these problems, work your way from the parts that you know the most about over to the part you know the least about. So whatever you know the most about, start there and carve it up. So ignore the rest of it, just decide what A is doing. Ignore the rest of it, just get the equations for what D is doing. And then for B, we're also going to have to add together lengths of rope to see how all those motions are controlling one another. Write in what the problem statement gives you. There's a velocity of D, and then A has constant acceleration. We're going to be using our constant acceleration equations over here, starting with an initial velocity. So just draw in all the information that the problem statement gives you. Okay, what piece of this should we start with? What are we given the most information about? Looks like we're given the most information about this little piece over here, A. So let's start there. And what are we told about A? Okay, collar A starts moving down from K with a constant acceleration. Yay, we have a constant acceleration problem. It starts with 0 velocity. So it starts from rest at 0 velocity. It accelerates at a constant rate. And by the time it gets to L, the velocity at L is 12 inches per second. Okay, so start from 0, accelerate up to 12 meters per second as we pass position L. Uniform acceleration. I think you can write up some equations that describe what's happening here. Here's the equations that describe what's happening. We have a velocity, we have a position. They didn't give us any time information, so that's why it's convenient to use this velocity position equation since we don't have time. So plug in final velocity of 12 inches per second, initial velocity, it starts from rest, is 0. It moves down 8 inches, so you have to study the dimensions off of the figure that's given here to get that information. So we have velocity, acceleration, position. We can solve for what acceleration happened there. So that's how fast that little piece A is accelerating. Now that we know that, we can solve for how long it takes from K to L. That'll be another valuable piece of information to have. So final velocity, initial velocity 0 plus acceleration times time. We have everything in this equation, okay? Final velocity is 12, initial velocity was 0. There's our acceleration, okay? So we can plug that acceleration in and solve for how long. So that's the time it takes from K down to L. The next little piece, this time let's look at part D. So what is D doing? The problem statement told us that D is also just uniform straight line motion, rectilinear, so linear, straight up and down. In this case, we have a 0 acceleration situation. So the position is just where it was initially, and we have a constant velocity problem. Now we can plug that time in we got from A, and we can see that D has moved 4 inches as A has moved 8 inches. So there's the position of D after A has moved all the way down to L. So see how we're just moving from one little piece of this puzzle to the next piece, and then the final piece will be part B. This is where we have to add together all of the chunks and see how they're related to one another. Get your highlighter out. We have one cable holding A up, okay? So this is the yellow piece. we have 2 cables holding D up. See that 2 on here? That's the green piece. And then it's only 1 cable holding B up. So change in X over here, 1, 2, 1 is the ratio we're looking at here. If we know how far A went, so A went 8 inches down, we know how far D went. Now we can solve for how far B is moving around. So 16. Think about the mechanical advantage here versus the distances that were moved. So we moved 8 inches for A, only 4 inches for D, but 16 inches. So B is over here moving around like crazy, while D just moved a little bit. That's kind of interesting, and that is tied into the mechanical advantage that goes with using those pulleys here too. Last little bit, so we have the relative positions. This turns into relative velocities. It also turns into relative acceleration. So here's the relative velocity. So A was going at 12 inches per second, D was going at 3 inches per second, and B is cruising. It is going at 18 inches per second, much, much faster than the other two. Walk from velocity to acceleration, we have the same ratios here. So 1, 2, 1, 1, 2, 1. We're just taking the next time derivative. And we have A is accelerating. We had to solve for that. Remember solving for that constant acceleration problem? D was constrained so that it was moving at a constant velocity. So D's acceleration was 0. So that means that B is accelerating at the same rate that A is. They're going in different directions. There's a negative sign here, but these two guys end up having the same acceleration, but very different velocities going on. Again, this is a 2 degree of freedom problem. We had to know information about A and information about D. Know information about 2 pieces of it in order to solve for what's happening for B. So 2 degrees of freedom. That concludes section 11.2 with some specialized cases and relative motion problems. So we went through constant velocity, cruise control stuff, solved a couple of constant acceleration problems, and then we extended that to analyzing the motion of several particles, whether those motions were independent of one another or dependent of one another, and looked at how the velocities and accelerations and positions were changing relative to one another. Rather than just relative to the water, it was relative to one another. And this all comes from these 3 main equations. Velocity is change in position with time. Acceleration, you can either get acceleration from change in velocity with time, or acceleration is velocity times change in velocity over change in position. So don't forget about this little relationship for acceleration too, where our constant acceleration equations come from. We'll see you next time.